Welcome back to Control System Lectures. In this video, let's talk about designing a lag compensator using a Bode plot. This video is a continuation of the series on designing lead and lag compensators. If you haven't watched the previous videos, I've put a link to the playlist in the description below where you can find the rest. I recommend that you haven't already watched them, you should start there, and then this video will make a lot more sense. In the video on designing a lead compensator using a Bode plot, I walked through a simple design problem where we had a system with a plant of 1 divided by 0.2s plus 1. And we needed to design a control system that gave us less than 2% steady-state error for a ramp input, and the system had to have more than 48 degrees of phase margin. The first two steps for designing the lead compensator were actually generic steps that we're still going to take when designing a lag compensator, so I'm going to repeat them quickly here. The first step is to determine if the system type is sufficient to meet your steady-state error requirement. In our case, since we have a finite steady-state error requirement to a ramp input, we need a type 1 system, or at least a single pole at the origin. So we added that integrator, 1 over s, to our compensator. Without this increase in system type, no amount of gain would ever allow us to meet our steady-state error for a ramp input. The error would continue to grow to infinity. And that's because our system is only a type 0 since there's no poles at the origin. Now let me draw our block diagram of our system so you have a visualization of what we're trying to do. We have our plant, and now we've just added a 1 over s to increase the system type, and that's part of our compensation. And now that our system is capable of meeting our steady-state error requirement, step 2 is to choose a gain that's going to get us there. And if you recall back to the other video, we came up with k must be greater than 49. And to make the math easier, we just chose k equals 50. So after our first two steps, this is what our system looks like. And if we were to implement this controller, 50 over s, and close the loop, we would meet our steady-state error requirement. But at this point, we've done nothing to meet our phase margin requirement. Which brings us to step 3, where we drew the Bode plot of our open loop system and our currently designed compensator to see how much phase margin we actually have. So this is the open loop Bode plot of our system. It's 50 divided by 0.2s squared plus s. And we find that we still only have our 18 degrees of phase margin, which isn't enough to meet our requirement. Now in the last video, we added a lead compensator to increase the phase margin. And the philosophy behind that design was to add phase to the system where you want it, without adjusting the gain at the point by too much. Which is exactly what we did. And we came up with a lead compensator that looked like this. We had a 0 around minus 11 and a pole around minus 45. But this is where I'm going to blow your mind. What if I told you that we could still meet our phase margin requirement by designing a lag compensator rather than a lead compensator? Essentially, we'd just be taking this pole and 0 and swapping them. Of course, we can't just swap them in their current place. There's a slightly different philosophy when using a lag compensator. And that's because if we just had them trade places, we'd be subtracting all of that phase right at that critical point instead of adding it, and we'd actually be making our system less stable. When using a lag compensator, we're trying to meet our phase margin not by adjusting the phase, but by adjusting the magnitude plot. You can clearly see that if we dropped magnitude, the gain crossover frequency would move to the left, which would increase our phase margin since phase gets further away from minus 180 degrees as you go further left. Now we can reduce magnitude by just reducing the gain of the system, but there is a problem with that. We've already set the gain of the system to meet our steady-state error requirements, which is determined by this low frequency region in the Bode plot. So how can we maintain the same low frequency gain while still reducing the gain at the critical region? All while not disturbing the phase plot too much, and that is with a lag compensator. Let's draw the Bode plot for a lag compensator and see how this is accomplished. Here's an arbitrary lag compensator, 2s plus 1 divided by 4s plus 1, and its corresponding Bode plot. Notice that when s approaches 0, or omega gets closer and closer to 0, the magnitude of this lag compensator approaches 1 divided by 1, which is 0 decibels. And you can see that clearly on the graph, that at low frequencies, the magnitude is 0 dB. And we want the DC gain to be 0 dB since we've already stated that we don't want to mess up our steady-state error, so this won't affect it. Also, as s approaches infinity, the magnitude approaches 2 divided by 4, or 0.5, which corresponds to minus 6 dB. And again, we see that clearly in the Bode plot. It's this unity gain at low frequency and attenuation at high frequency that is exactly what we're looking for in our design problem. Oh, a real quick side note. This lag compensator has a 0 at minus 5 and a pole at minus 0.25. But that doesn't mean that you can write the lag compensator as s plus 0.5 divided by s plus 0.25. Sure, both of these have a single pole and single zero in the exact same place, but their gain is different. With this second method, as s approaches 0, the gain approaches 2, or 6 dB. And as s approaches infinity, the gain approaches 0. So essentially, we've just increased the gain plot up by a factor of 2, or 6 dB. And this is obvious when you try to do the math to convert from one to the other. Multiply the numerator by 2 over 2 and the denominator by 4 over 4, and we're left with our mysterious gain of 2. Because if you leave out this 2 divided by 4, you're effectively doubling the magnitude of the system. So I'm going to stick with the first way that I wrote it because I think that it's cleaner, but you can write it either way as long as you keep track of the gain. Okay, now remember that our goal is to reduce the gain in the system, but without affecting the phase too much. And looking at the Bode plot of the lag compensator, it should be fairly obvious which frequency section will accomplish that. It's this section that's the higher frequency off to the right. Up here you get large negative gain and relatively zero phase shift. So when we choose the locations of the pole and zero, we want to do so in such a way as to put this section of the lag compensator over the region of our system's Bode plot that we're trying to adjust. And we do that by pushing this large phase lag portion to as low a frequency as we can handle. Okay, let's get back to designing the lag compensator to meet our phase margin requirement for our particular system. Here's the Bode plot of our compensated open loop system. Again, we only have 18 degrees of phase margin and we need at least 48 degrees. So step 3 of our lag compensator design is to determine at which frequency the phase would meet our phase margin requirement. And then figure out what the gain is at that frequency so that you can determine how much you need to drop the gain by in order to make that the new gain crossover frequency. In our case, it's about 18 decibels. But since the lag compensator doesn't add exactly 0 phase shift and exactly the magnitude we want, then it's usually a good idea to add a small safety factor to our phase margin. So I'll drop the gain by 20 decibels, or a factor of exactly 10. This also has the added benefit of making the math easier for this video. In your projects, you might have to try a couple of factors before you settle on the one that you like best. And if we look back at our lag Bode plot from above, the gain is reduced at high frequencies by a factor that is equal to the ratio of these two numbers, the numerator and the denominator. So in order to drop the gain by a factor of 10, I need the lower number to be 10 times larger than the upper number. So that sets the relative ratio between the two. So how do we pick where to place the pole and the zero now that we know that the relative ratio between the two needs to be 1 over 10? Well, remember that we want our negative phase lag to be as far left as possible, which means placing the zero and pole as close to the imaginary axis as you can, or making the number tau as large as you possibly can. The larger you can make this number, the less the lag compensator will interfere with your original system. Remember, this is the same philosophy we used when placing the pole and zero when describing how we designed a lag compensator with root locus, always as close to the origin as possible. And just like before, there is a limit to how close you can move it because you start to get to a region that is physically impossible, or at least really difficult to make in real life. So the rule of thumb is to place the zero about 50 times closer to the origin as the dominant poles. So in our case, it would be 50 times 0.2, which is 10. So it would be 10s plus 1 in the numerator and 100s plus 1 in the denominator. And that completes our compensator design for this system. We have our lag compensator, plus the gain that lets us meet our steady state error, plus our integrator to increase the system type, and of course we have our original plant for our system. So these 4 blocks represent our open loop system. Of course we would feed back unity gain on the output and compare it with a reference at the beginning to generate an error term, and this would be our closed loop system. And this closed loop system should meet all of our requirements, but we can test that in MATLAB. So the first thing I'm going to do is define the systems to our workspace. And I'm going to start with our partially compensated system, which has the 50 over S, but no lead and no lag compensator. Then I'll define the lead compensator, which we generated in the video before. And finally, I'll define the lag compensator, which we just created right now. And now I'm going to plot the Bode plot for our partially compensated system alongside with our lead and lag compensated system so that you can see the differences between all three. Now let me add a legend real quick, but you can see that the blue line is our partially compensated one with 18 degrees of margin. Our green line is the lead compensated system, and the red line is the lag compensated system. And if you right-click and select Characteristics and then Show All Stability Margins, it'll show you the phase margins for all three systems. And check this out. Notice that the original system has a phase margin of 18 degrees, like we thought, but both the phase lead and phase lag compensated systems have about 50 degrees of phase margin, so they both meet our requirement. The other thing you should notice is that at really low frequencies, the DC gain hasn't changed for any of them, which means we haven't messed up our steady-state error requirement. But perhaps the most obvious is that the gain crossover frequency was increased for the lead and decreased for the lag compensator. And the gain crossover frequency is related to the speed of a control system. So essentially, we've slowed down the entire system so that it no longer reacts as quickly. And this will be obvious if I plot the step response to each of the closed-loop systems. First, though, I have to generate the closed-loop system in MATLAB using the feedback command. And then I can plot the step response for all three of them on top of each other, similar to what I did with the Bode plot. And there you go, you can see all three systems. The blue system, which was the partially compensated one, has only 18 degrees of phase margin, so it's a little bit less stable than the other two. But you'll notice that the green, the lead compensated system, not only is more stable, but it's also fast, and the lag compensated system is equally stable, but a little bit slower. Pretty crazy, huh? So now you might be saying, well, why the heck would we ever want to slow down our control system? Don't we want it to be as fast and awesome as possible? Well, maybe, but it depends on what your system is designed to do. If your system doesn't need to react very quickly, or you're not sending high-frequency commands to it, it's actually a better design to slow it down, because then it won't react to high-frequency noise as much, and that'll make it a less noisy system. Also, if your system has unknown or poorly modeled high-frequency modes, then by slowing down the system, that model uncertainty won't affect you if your system isn't even able to respond to those high-frequency modes. So all in all, both methods, lead and lag, have their benefits and drawbacks, but by understanding them, it'll help you decide which method you want to use when designing your control system. Now, I hope you guys enjoyed this mini-series on designing a lead and lag compensator. I'll try to use these techniques when designing controllers for my projects in the laboratory videos to give you some extra exposure to them. If you have any questions or comments, please leave them below and I'll do my best to answer them. Don't forget to subscribe so you don't miss any future videos, and as always, thanks for watching.